Okay, well, let's continue now and talk about a polarizing interferometer. So this will be an interferometer that uses polarizing beam splitters to split and then recombine a beam of light and exhibit interference phenomena. It's a really neat instrument, and it features into our first first three quantum optics experiments. Here, let's go to the whiteboard. Here, let's sketch out what the system looks like first, and then we'll look at it in more detail. So to start, our system should have a source of light, which will be a laser or other monochromatic source. Then we'll add a polarization rotator, a half-wave plate, so we can control the polarization of the light beam. And after that, the light is going to reach first a polarizing beam splitter, okay, which I've drawn here. And the point of this is that when light strikes the polarizing beam splitter, it's either reflected or transmitted according to its polarization. For example, suppose that the light exits the polarization rotator and it has a polarization pointing in the 45-degree direction. When it strikes the polarizing beam splitter, one component, let's call it the vertical component, will be reflected, while the other component will be transmitted. Okay, polarizing beam splitter. After this, we're going to bring the beam to two mirrors, one here and one here, and the beam will be reflected up and recombine. Excuse me. And at the place where they would cross, we're going to put a second polarizing beam splitter. There we are. Okay? So, polarizing interferometer. Now, you'll notice that just to illustrate what we were talking about before, in this case, light of one polarization, we said vertical, is reflected from the first beam splitter. That propagates through, and then we'll set things up so that when it reaches the second beam splitter, it's also reflected. On the other hand, light of the horizontal polarization is transmitted by the first beam splitter, and it's reflected, and it's also transmitted by the second beam splitter. So these two components of the polarization are split apart at the first beam splitter and then recombined at the second beam splitter. Only importantly, they might travel different distances to go from the first beam splitter to the second beam splitter. So when they recombine, they might recombine out of phase. Okay, that's what we'd like to describe. And you can imagine that this leads to interference. And we'd like to look at that in more detail. So now we'll turn to equations. Just one second. Okay, now to begin with, if you'll indulge me, it'll be simpler if we can represent the electric fields in this system with complex fields. That means that the electric field vector at some moment in space and time can be written this way. It has an amplitude, we'll call it E0. Then it has a phase, e to the I theta, and then it has a direction of polarization. Here, just as in our earlier discussion, the phase is just a shorthand for kz minus omega t. Okay, so the phase varies with position and with time. And here, I just am taking z to be the propagation direction. And it's a little sloppy because when the propagation direction changes, I'm still calling it z, but don't worry about it. The polarization direction here is a vector, a unit vector. And so, for example, for horizontally polarized light, n would just be a unit vector pointing in the x direction. And for vertically polarized light, it would be pointing in the y direction. Well, we can have more complicated situations, like this one. What direction does that point? If you think about it a moment, it's a combination of vertical and horizontal, so it would be linearly polarized at 45 degrees. Okay? And we could have other combinations as well. Here's something interesting. That looks kind of weird. Now my vector is x, is 1 over root 2 x hat plus I times y hat. That means that the y component is, if you like, delayed by pi radians from the x component. Okay? If we think about what the complex fields mean. It looks strange, but this is allowed in our complex notation. And what this would mean is that the light would be left circularly polarized, which I'll write like that. Whereas this would be right circularly polarized. Okay? And this would be a more general case here. Let me rewrite that. It wasn't so clear. Oh, I'll just start over again. Here, the unit vector is 1 over square root of 2 times x hat plus e to the I epsilon y hat. And this would be a more general state, elliptically polarized, where the phase difference between the x and the y components would be given by that epsilon term. Okay? All right. So we're going to continue to talk about the polarizing interferometer, but we're going to use this complex notation to do so. Here, let me stop for a moment.